Coriolis effect is still going to skew things off clockwise, only this time now, clockwise is toward California, not out into the ocean. So now water's piling up along the coast. So I've got a hill. That's not going to work either. Gravity's going to pull that water back down flat, and in doing so, water's going to be sinking down into the depths. So something as simple as wind direction combined with Coriolis can change whether I've got water moving upward or downward, upwelling or downwelling in the system. Why should I care? Well, a couple of big things. Downwelling in general just helps get gases down into the ocean. So oxygen for fish that do respiration gets mixed in and gets driven deeper in the ocean. So it's a good thing for fish. But when it's upwelling, what it's doing is it's bringing nutrients that are sinking down through the water column to accumulate in the sediments at the bottom. It's getting those stirred up and brought back up to the surface, and now there's more food. And it's a favorable area for the fish to go and really, have buffet time. So they're just excited. They're out there like crazy, feeding on all this extra food that's getting mixed in, and now fishing is phenomenal. So no surprise that all along the California coast, the South American coast along Peru and Chile, great fishing when they've got upwelling, because all this extra food is getting stirred in, brought back to the surface. Good fishing. But boy, when the winds shift, when things change and downwelling takes over, those fish still need to eat. They go someplace else. They're still looking for food, and it's not there. So all of a sudden, places like Peru, that fishing, commercial fishing, counts for a major portion of their economy, man, it gets shut off for a couple of months and the whole economy just plummets. So they have their problems then as these patterns change. Now that's all kind of what's happening on the surface and up and down from the surface to the deeper part. But what's driving water down in the deep part? It's not the wind, which is driving all the surface circulation. It's how do you get wind down into the ocean? You don't. It's only going to affect the surface, isn't it? So if I've got circulation happening in the deep part of the ocean, something else has got to be driving it. It's not going to be the wind. And sure enough, we see this, and it's back to the old thing we talked about fairly early on, this idea of density differentials. If I take water and I cool it, colder water is going to be denser than warmer water. If I add salt to the water, salt water is going to be denser than fresh water. So if I take salty water, stick it down by Antarctica, what have I done? I've just given it the double whammy, right? It's salty, it's really cold, it's some of the densest water in the ocean, and it's going to sink. Now, if it's sinking, where's it going? It's not like there's a big void down there. It's got to displace other water. And that other water starts moving out, moving toward the equator, where, as that water warms up, it's becoming less dense, isn't it? So at the equator, the water tends to be rising. At the poles, the water tends to be sinking. And the overall pattern that we see is what we call thermohaline circulation. Thermo for temperature, haline for salt. That density difference as we make things colder and saltier drives this system. And that's how we move water in the deep part of the ocean. Completely different than moving water in the top part of the ocean, where we're pushing it around with the wind. So if I look at it, the very densest water is being made down here by Antarctica, And it's creeping along the bottom, and it is exactly what it sounds like. It's bottom water. And it's a very small amount of the water, but it is so cold, so dense, so salty, that it just hugs the bottom and moves along there. Even the water being made up by Greenland and Iceland in the northern part of the polar areas isn't as cold and dense as that being made down in Antarctica. It still is cold, it's still dense, it's still moving along, but it's making up the majority of the water called the deep Atlantic water. We don't see this effect quite as pronounced in the Pacific because the Pacific is so much bigger that it kind of mutes this effect. The surface water, which represents about 2% of the surface, is warm, oxygenated water that's sitting right on the surface. In this diagram, I couldn't draw this black pencil line thin enough to represent how thick that layer is. Okay, so it's really 2% of the ocean waters, not a whole lot. And that's the warm, fun part of the water that we like to go swimming in. So we see these different layers, these different water masses based on salinity and temperature, and they're moving around and sinking, going down, downwelling, rising, upwelling in various parts of the ocean. So, how would I make water saltier at Antarctica? I can make it colder, it's just so friggin' cold down there, right? But how am I going to make the water saltier? How about if I just freeze the water? I start making a big ice shelf, like the Ross ice shelf. When I freeze the water, I'm only freezing the H2O, the water molecules. The salty stuff, the ions that are dissolved in the H2O, kind of being left behind. A few get incorporated into this structure, but for the most part, that gets left behind. So it's just the H2O that I'm freezing. So as I make ice, that means I've kind of removed water from the basin and tied it up as ice. So the remaining water has all the salt still, so it's relatively getting saltier, isn't it? So as I get that water colder, I'm also making it saltier just because it's so much colder. So there we go, thermohaline circulation. So if I look at the circulation patterns on the surface and the circulation patterns in the deep part of the basin, they all hook together, but they're not the same. If I look at it through the Atlantic, deep water is moving along through the Atlantic, kind of coming down from the Greenland area, moving down through, coming in, mixing in the southern part. I've got water that's always moving along in the circumpolar current here around Antarctica, as is happening on the surface. So that's a pretty major effect. And in the Pacific, you can see some of this cold, deep water spinning off into the basins of the Pacific. It's actually warming up and coming up into the surface water, joining the gyres and moving around in the gyres. So I've got the one pattern on the surface. I've got another more north-south pattern happening in the deep. So in the surface circulation, I can move water around through that in a matter of just a few weeks. The deep circulation, I'm talking hundreds to thousands of years. So these patterns mix, but different depths, different patterns, different time frames. Okay. So we said that the spinning of Earth on its axis provides this Coriolis effect, but the axis is also tilted. And as that revolves around the sun, what we see happening then are the seasons, right? And right now, we're kind of sliding past fall, and we're heading into winter. And what's happening is the tilt of the axis is such that now the northern hemisphere is tilted away from the sun, the southern hemisphere is tilted toward the sun, so the southern hemisphere is having a nice toasty summer, while the northern hemisphere is having a chilly winter. And that's kind of where we're headed. Right now, in fall and in spring, the tilt of the axis doesn't matter too much, because here's the sun and the tilt isn't toward or away from the sun, it's parallel to the sun. So as we swing around now to summer, here the axial tilt has the northern hemisphere toward the sun, the southern hemisphere away from the sun, such as flips. When we're having summer, the Australians are having winter, back and forth. So we're seeing this change now of seasons. This is kind of a good thing. It allows for crops. And we'll see when we talk about weather patterns how this is kind of going to affect civilization a little bit. It's this relationship now of the Earth and the Moon and the Sun, the planetary, the attraction between these planets and the Sun, moons, that are going to create the biggest waves on Earth. And these are known as tidal waves. Now, you've probably all got the idea of what I just said is these waves that are big giant waves that come out of nowhere that wipe out the poor little South Sea Islanders, all trying to climb up the one palm tree as the tidal wave comes in. That's not what I'm talking about. I'm talking about tides. Just the daily occurrence of the water level coming up, going back down, usually in places a couple of tides a day, a couple high tides, a couple low tides. That's the tidal wave. Okay? What everybody kind of thinks of in the way we used to talk about tidal waves are what we now call tsunami. Okay, so the terminology's changed in the last 15 years or so. So remember back when we made the solar system and we started going through that accretion process and the planets started to form, and as we made mass and we made bigger bodies, there was more gravitational attraction. So the more mass you have, the more gravity you get. The other component of gravity is the further away that the bodies are from each other, the less attraction there is. So when we send men to the moon, we get to a point where the space capsule is far enough away from Earth that Earth essentially has no gravitational attraction on that space capsule anymore. And as it approaches the moon takes over and has gravitational attraction, but not as much as Earth, because the moon's a lot smaller, so less mass. Okay, so we have two relationships going on here. One, bigger the mass, the more the gravity. The other is indirectly proportional. The further the distance, the less the gravity. So let's look at the Earth, the Moon, and the Sun here. Earth, moderate. Moon, small, but right next door. Sun, giant, 99% of the mass in our solar system, but way, way far away. So which one do you think is going to have the biggest effect here? Well, let's go back. You'd think the moon would have a lot of effect because it's so close, so that relationship, but the sun is so big, 99% of the solar system's mass. Man, a lot of mass, got to have a lot of influence, right? But it turns out, despite the fact that the sun is so huge, it's so far away that the moon actually has more influence on our body, our planet. Now the moon does two things. Number one, it helps stabilize Earth on its axis. The axis wobbles a little bit. but only about a degree. It goes from about 23.5 to about 24.5 degrees of tilt. Now, that's a good thing. If the Earth didn't simply keep rotating on that stable axis, it would just be tumbling around in space, right? Now, if that were the case, how would we ever have any logical seasons? How would we be able to grow things? Now, what worked one year won't work the next because Earth is flipped over in another direction. We're not in the same climate belt. So by staying, rotating around our axis, and that axis staying at about a 1 degree tilt, plus or minus, everything keeps lined up. Everything stays lined up. Seasons come and go, come and go. And we can plan on growing corn here again next year. So stability, just keeping the Earth stable is a big thing. The other thing that happens is we get tides. If you look at it, the gravitational pull between the moon and the Earth, the moon is actually kind of pulling the ocean off of planet Earth. It's attracting that water and kind of pulling it toward the moon. Yeah?
What makes the being like near the equator so hot year round, even though like the distance from the sun isn't changing much?
Well, the simple fact that the equator is getting a light beam directly on it. A meter of light beam hits a meter of land and warms that up. Okay, it's almost coming dead on. As I go toward the poles where it's curved, or the curve becomes, instead of flat to the beam, it becomes more angular to the beam, that beam comes in and it spreads out over a much larger part of the globe. So that might shift north and south a little bit with the seasons, but the equator is always going to be about the same. Okay? Check in the after class if you still have a question.
No, it makes sense.
Yeah, okay. And we're going to kind of see that same kind of thing going on here with the tide. Okay, here's my moon. Notice gravitational attraction, and the moon is pulling the water off of the planet a little bit. So I've got a high tide. It's like the crest of a wave. Notice on the other side, I've got another bulge of water. And I've got a couple of things going on there. One is the moon's not only pulling water off the front side of the moon toward the moon, the front side of Earth toward the moon, but it's also pulling Earth away from the water on its backside. Now, that's not as big as an effect as the water on the front side here. This is obviously closer to the moon, and it's going to have a bigger effect. Pulling Earth away from the water on the backside, not as big effect. So there's something else going on. What we basically are seeing is this effect that as Earth spins, it is spinning not just about its axis, but it's also spinning with the moon. So the moon and Earth are acting as a single body, a system. And that means that if I were to balance this about its axis, the axis is not the axis of Earth. That only accounts for Earth. If I throw in the mass of the moon, that's going to shift the center rotational point a little closer to the moon. So the whole system revolves around a point that's actually kind of part way from the center of Earth to the edge. Something called the Berry Center. So when Earth is rotating, it isn't making a nice circle, but it's kind of doing scallops because of that pole being shifted. You have to think in terms of the moon. So what we end up seeing now is this basically causing water to be thrown off the backside of Earth by momentum. And that adds to this whole principle. Okay, so there are a couple things going on here that get kind of hairy. All right, I'm not gonna hold you to that.